Okay, Harry.
Hello, hi, everyone. Good day. Welcome and thank you for joining the Geoscience and Geoenergy webinar of today, 11/11/21, 11th of November. So it's very close to conclude this year. It's November. Today, we have the pleasure and honor to host our dear colleague and good friend, Phil Vardon, from TU Delft Geoscience and Engineering Department, exactly where I also work. Phil's office is a few floors downstairs. I am on third floor. Phil is on first floor, I think.
It depends where you're from, Hadi. It's first floor if you're American, and it's ground floor if you're English.
Exactly. Yeah. So I read a few lines about Phil. He would not need my introduction. Though Phil is associate professor in the Department of Geoscience and Engineering and leads the theme called Geothermal Science and Engineering. In this function, as lead of the geothermal theme, he leads the scientific program on the campus deep geothermal well, which is being developed. Phil's research is on the impacts on geomaterials of various processes, including heat, moisture, and containment in movement, including practical applications such as geothermal energy, obviously, and also heat storage and radioactive waste disposal. He is the TU Delft PI, Principal Investigator on the Campus Geothermal Well, the nationally funded energy piles in the Netherlands project, and the ATES, Aquifer Thermal Energy Storage, triplet project. He was a chair of the Energy Geotechnics Conference held in Delft in 2019 and also a co-chair of Interpor, International Society for Porous Media Conference in 2017 in Rotterdam. Phil, thank you very much for graciously accepting our invitation. It's a pleasure to have you here. You have helped us co-host this webinar in the past as well. To the audience, please note Phil's lecture would last for about half an hour, followed by questions and discussions. Like always, please do type in your questions in the chat box, and Sebastian will go through them and have the questions being addressed by Phil. Please do not wait until the end of Phil's lecture to ask your questions. Please do type them whenever you feel appropriate, because your question may trigger other colleagues' question as well. So it would motivate others to also ask questions. And I'm sure Phil, as every other professor, would welcome your questions from all aspects of his talk. So without any further ado, Phil, we are all looking forward to hearing your lecture. And thanks once more for this.
No problem. Thanks, Hadi. Thanks, Sebastian, for the invitation. And so what I'm going to talk about today is a sort of a presentation of some of the things that we're trying to do on campus and around campus, all about pilot cases and trying to do what I call developing an urban energy laboratory. So probably you'll see in this presentation, there's some sort of big themes. What that means is there's details missing, and it means that also several colleagues have been involved. So I'm not going to take all the credit for myself. I'm just the person sort of shouting at you today, trying to give you some of the information. A little bit of motivation of why we're trying to look at sort of geothermal energy in the Netherlands. I mean, especially it's a topic worldwide, but let's use the Netherlands as an example. This is the final energy consumption in the Netherlands. And I think most people, when you talk about sustainable energy, think about changing their light bulbs, think about wind turbines, and fairly recently have started thinking about Teslas. And I would say that if you see from this figure here, you can see that actually most of the energy is to do with heat. And that's to do with heating our houses, to do with having showers, to do with cooking, all of these kind of things. And actually, if we get rid of all of our fossil-based electrical energy, we still have almost as big a problem as we did anyway. So it's a relatively smaller component. So heat's the biggest component. If we have a little look about how we're doing in terms of turning these different components renewably, you'll see that we're doing pretty terribly all round. And you'll see that actually heat's doing the worst. So if yeah, I mean, heat has about 3% of the total energy is now renewable, and that means we're doing incredibly badly, which means we actually have lots of opportunity to do new things. So that's a bit the motivation of where we are. What you can also see is electricity and transport has a long way to go, but proportionally they're doing about twice as well as the heating sector, if not slightly more. Let's have a little look at some of the sort of characteristics of heat use and electricity use. And this is just a typical building. This is actually a building in Amsterdam where these things come from, but this is it could be any sort of typical urban building. And if you look at the electricity usage over the year, it's moderately constant. It has some fluctuations. Of course, it has daily fluctuations, but it has relatively constant profile over the year. Whereas if you look at the gas usage of a typical building, or the heat for a typical building, you have something that you see quite different. You have this really strongly seasonal characteristic. So of course, in the winter, we really push heat into our buildings. In the summer, in the Netherlands, we don't really need cooling. So that's why you see the electricity usage is fairly constant. And we have a virtually zero heat usage during the summer months. Some of this, and it depends on how you heat your water for hot waters and showers, etc. Sometimes it drops to zero and sometimes not. Now, often what we do is we have electricity usage in kilowatt hours or in joules, and we have gas usage in meters. I've put them in the same units here to show you a comparison, and I've stacked them on top of each other here. And what you can see is actually the energy use that we use for heating outweighs quite considerably the energy use that we have for electricity. So it means there's a big challenge. It means that we've got a seasonal challenge. And just to hint towards some of the solutions, I put a fourth figure here that showed what we could do if we used a typical heat pump-based system to find renewable energy. And actually, we can flatten this profile considerably, as well as, of course, reducing the overall heat input from primary sources. Okay, so that's just a bit of background of how heat usage is typical. A few sort of characteristics, and I've called it the trouble and the joy of heat. One of the things with heat is that the quality, and what I mean by quality is basically the temperature, is really important. And changing these kind of temperature levels can be quite difficult. So it's not like with electricity where we have a sort of a transformer, and of course there's details in this, but it's relatively straightforward. Actually, changing the temperature level often requires quite a heavy input of energy, and so heat pumps is the system that typically we use to do this. Transport is also quite difficult. It's quite difficult to transport heat over any sort of medium to large distances without quite heavy losses. And that means we have to think about whether those losses are acceptable in terms of our overall system and how we can minimize them. And of course, as you just saw in the annual demand, there's huge seasonal differences. And that means that you have some challenges in terms of matching heat generation and heat demand. In the summer, there tends to be lots of heat available and almost no usage requirement. And in the winter, the opposite. So this leads towards a challenge in terms of things like storage. But then you've got what I call the joy of heat. And heat's everywhere. So wherever you are, there's some heat available. There's heat available outside. There's heat available in the ground. There's heat available in the water. And that gives us quite a lot of opportunity to do different things and to play a bit with the systems, play a bit with the levels, play a bit with all these different aspects. It means there's some more challenges in terms of multitudes of possible systems, but it's available. So there's some things we can do. And also one of the other things is low quality heat is still useful. And so I think probably most people know is there's a drive towards driving down the temperatures that we need to have to produce our space heating. And that's because you can still do useful things with really quite low temperature heat. So in terms of different kind of geothermal systems, and that's mostly what I'm going to talk about today, there's a range of systems. And this is just a sort of schematic, and it doesn't really cover all of them still, but it covers the main ones. This picture is made by a colleague of mine, Martin. But from the left to the right-hand side, what we see is a borehole thermal energy systems or ground source heat pumps or different variations upon the same system where you have closed loop systems. So you have basically plastic pipe going into the ground, circulating a fluid and having some sort of heat exchange with the ground. Tends to be fairly low temperature and tends to be suitable for very small buildings. You also have aquifer thermal energy storage systems, which are really common in the Netherlands and much less common anywhere else. I think there's about 3,000 systems in the world and about 2,900 of them are in the Netherlands. But this offers the opportunity of storing your heat and your cool or your absence of heat at different times of the year to supply a kind of a balanced heat profile to larger buildings or small communities. I'm just going to jump right to the right-hand side for a second. There's what we typically recognize as deep geothermal energy or deep geothermal direct use heating, where we would take out heat out of the ground, be able to use it directly at relatively high temperatures. And when you talk about high and low temperatures, there's always some differences of opinions and differences of definitions. I'm talking about high temperatures for heating, so lower than 100 degrees, but warmer than, say, 70 degrees. So in this schematic, it has 90 degrees, and then re-injecting the same water when you've taken the heat out of it. And then I come one step further back to the left, and this is where we have high temperature ATES systems. And normally this is used in conjunction with a heat source that's relatively constant, such as a geothermal well, where you store higher temperatures at a much shallower depth, probably, that you can then balance your demand profile. Okay, so they're the sorts of different systems. And on the TU Delft campus, we're trying to install a number of these, partly for practical reasons. We need to have a sustainable energy supply for our campus, but also for research reasons, to try new systems, to try to integrate systems and to do really detailed research if possible. So this is just a sort of a few things of what we're trying to do on campus. And what I'm going to focus on today is two sort of extremes. So I'm going to focus on very shallow geothermal systems, so at around 20 meters deep. And I'm going to look at a deep geothermal system around 2 kilometers deep. Although we have plans of all for different systems, and we have certain different systems installed, I'm going to kind of focus on the two extremes to give you a sort of flavor of what we're trying to do. So the first thing I'm trying to do is we're looking at energy geostructures. And what an energy geostructure is a heat exchanger combined with a structure, so something that has a structural purpose. And in this picture, it's a pile, so a foundation system. You put a heat exchanger in a foundation system, and you utilize a heat pump, much like you would use a borehole heat exchanger or a ground source heat pump type system. The big advantage of these systems is you don't have to pay for an additional borehole or additional set of boreholes. So it's much cheaper to install. It's about the same cost as a normal gas heating system. So it eliminates one of the barriers of accessing sustainable heating. I'm going to talk about one specific type of energy geostructure, and it's an energy quay wall. It's a bit of a particular Dutch flavor of a project. And we have lots and lots of canals, lots and lots of waterways, and often inside our urban areas as well. So there's a system we've been working on with a small consortium of partners, which is to integrate these heat exchangers with these quay walls. You can see on the right-hand side of the slide the sheet piles they're made of, and effectively your heat exchanger is welded onto these before they're installed. So it's installed in exactly the same way you would normally install the piles, and yet you can connect it into a heating system. This leads us to quite some different engineering challenges. This leads us to, well, having to know the thermal properties at depth, which sounds really straightforward, but actually there hasn't been methods to do this in any reliable way until recently. We need to know about the material behavior because, of course, the main purpose of these structures is a structure. We need to hold up the quay wall. It needs to have a certain strength. It needs to have a certain behavior. And we need to make sure that using these as an energy infrastructure means that we don't change that. Of course, if we understand the behavior, we have to turn it into material models. We have to turn it into design tools. And I think what's also important, especially now that we want to go through a fast energy transition, is to know the field behavior at a large scale rather than just doing small scale kind of experiments. And that's what I'm going to talk about mostly today. We're doing work on all of these other boxes, but I'm just going to focus a bit on the field behavior in this lecture. So we've installed a field test, and you can see on the left-hand side what it looks like in the field. We installed a sheet pile wall exactly as you would normally do so, and you can see the tops of these welded pipes that have fittings into a sort of a plastic PVC pipes that can turn it into a sort of a heating network that uses the first of all the canal and the ground underneath as a heat exchanger. So what you can see is that, first of all, there's a schematic in the top right-hand side you can see here. What we have on the left-hand side is our canal. This is one of the main canal that has quite a lot of shipping going up and down it regularly that goes around the side of Delft. And then what you see is the sheet pile wall that was installed here, and that just provides the bank of the system. And there's a flood protection dike behind it. And this sheet pile goes all the way through the first, about 3 meters of water, and then down to 15.5 meters into the ground. So it's a fairly substantial portion is actually in the ground rather than just in the water. We wanted to try out a number of things. So we have a fairly complicated system, energy system that we installed, and we have what we call shallow activation, which means we only have heat exchangers in the water part. We have deep activation, which means we have it activated from the surface right the way to the bottom of the pile. And we also have panels that fit on for post-installation into old sheet pile walls to try to have a fast renovation of these different systems. And what we've been doing over the last about a year and a half is playing with them all, testing everything out and seeing what actually happens in reality. I'm going to skip over that. So, of course, we can just play with things and find the heat output, but that's not particularly good science. So what we've actually done is installed a fairly complex set of instrumentation. So we have some of these poles that you can see here and here, which have temperatures throughout the ground, because of course, if you're taking heat in and out of the ground, you're affecting the ground temperature and the water temperature. We have flow measurements, flow meters in all of the different loops, so we can understand what's happening within the system. We've also been looking at the flow rate in the canal, and then of course we've been examining how much energy we can generate, etc. Now, what's always tricky with field tests is that the environment kind of does what it wants. So that means that we can test all these different systems, these different parts of the system sequentially, but of course the outdoor temperature is changing as we're going along in time, and all sorts of other things are changing. So one of the things we had is fairly soon after we installed the system and had it working, we had a period of about 2 weeks when everything froze and it got down to minus 10 degrees. And in fact, the canal started freezing over. That was actually particularly interesting for our research, because we actually showed that we could generate useful temperatures even when it was useful energy, even when it was minus 10 outside. So I'm just going to show you a little bit of some of the results, and I'm going to keep this sort of analysis fairly qualitative, and I'm going to show you a little bit of how we've modeled it later. So we had some different phases where we looked at looking at, first of all, I say sort of different densities. So we had double loops, so that's twice the intensity, just the shallow activation, so just inside the water. We then looked at the same thing with different flow rate internally. We then looked at what would happen if we half the density of the loops. And then we looked at what would happen with the deep loops. So what happens underneath the soil as well. And then what's also interesting is because you look at the soil and the water, you have quite a strong storage component. And so we then looked at what would happen if we stopped doing anything. How fast would that heat escape again? So is it available for our use afterwards? And could we then actually pump in some extra heat and then store it for when we needed it later? So we had these different phases, and you'll see on the figures later, they're labeled from 1 to 4, where we're looking at the different types of system. What I show at the bottom of this figure here is the external temperature. And so you can see the line that has the sort of most detail in it is the measured canal water temperature that we observed. The lines that go over the top are the averages from past years' sensors, where they have a measurement every month or so. So you can see that the overall trends are fairly typical, but what we actually get is some really significant fluctuations around it. What you can also see, as I told you, in February, just after we'd started, we had a period where it got to about -8, -10 outside occasionally. But within the water, the latent heat manages to buffer this, so it never gets below 1 degree, which is one of the reasons why there's still some a fair amount of heat that we could take out. What you can also see above is the amount of energy that we got out of the different phases. So what you can first observe is that it follows a bit the external temperature. So you can see kind of the trends, and especially this kind of dip where it got very cold. You can see this back in the results. And you can also see that, we can generate quite substantial heat from, so this is sort of 4 or 5 kilowatts from a relatively short piece of key wall. So it can be a useful system. So of course, we've been analyzing all of these different things. But let me show you a little bit more as we go forward in time. So this takes us up to the end of where we're actually generating heat with the system in the first measurement period. And then what you can see afterwards, so this is the end of the water measurement period here at the end of 3. You can see phase 3 here is when we first use the deep activation, so when we first go into the soil. And what you can see is that here you see all of the ground temperatures. So sequentially through the ground, from purple is the most shallow and yellow is the most deep. You can see that there's a significant deepening of the lowering of the temperature as we extract heat from the ground. And if we go forward into the regeneration phasing, what you first see is we did what we call passive regeneration, which is a way of saying we did nothing. So we stopped the test, and we didn't circulate any water through the loops. And the idea of this was to test whether heat would just disappear quite fast naturally, or whether it would be available for use. And what you can see is, of course, some of the shallower parts start to warm up slightly as the water above is quite warm, but the parts at depth really stayed quite constant. This also coincided by chance, not by design, with a period of extremely warm weather. So the water temperature you can see here went up to around 22 degrees finally over a period of just 2 weeks. It warmed up from 10 degrees to 22 degrees within 2 weeks. After this period, we did what we call active regeneration. And what this meant is we simply circulated water around the system to see whether we could basically capture the warm water from the canal and put it into the ground. And what you can see is that we could store quite substantial amounts of heat fairly quickly into the ground. And as you would expect, you get this sort of steady decline in the amount that you can store as time goes on. Okay, so we looked at this. We quite liked the overall sort of results, and we can get energy, all those sorts of things, but we need to actually, that's not very good science, as you can imagine. We want to try and quantify this. And we tried a bunch of different things, and we tried some FE modeling, et cetera, and I have to be honest, the FE modeling didn't work that well. And then we came up with a very straightforward model, which is just a pipe in an infinite medium, and basically have just a loss or a gain from the pipe, depending on the water in, and then integrated it over the length. And certainly in the components, the phases where we just had the shallow activation, our model results and the power measured were surprisingly good with such a simple model. There's some details in this that could be explained a lot further, but I still have a number of slides to go, and I still see that the time is running on. We then extended this model into the phase where we had also soil, and we had to have a slightly more complicated fit, but the basic feature was we had different pipe sections, whether they were in the water or whether they were in the soil. And in the soil, we needed to have a superposition system because, of course, the soil has the history of what's happened where the water basically convects away and you get a refreshing of the water constantly. And what you can see is that, yeah, you get certain different features. You have the feature here where, yeah, first of all, if you switch it on through the soil, you get a lot of energy. And as the soil starts to cool down, you have to have the heat conduct through the soil, and that decreases as you go through time. You can start to separate these different components into the different parts in the model. And what was quite interesting in this specific phase is you also had some external temperature changes. So we actually went from a period, and if I show you the gray figure here, this is the gray is the total component that comes from the soil. So to start with, virtually all of the energy comes from the soil. And then as time goes on, it gets less and less. And you actually get to a period where we're storing energy in the soil from the water. And this was mainly to do with the time of year that we were doing it, where the water was really warmer than we needed. So actually we were taking energy out of the system, but also storing in the soil at exactly the same time. So I think that model's nice to be quite simple. And it also allows a bit of information about the working of the system. Okay, I'm going to move on from something that's very shallow into something that's quite deep. And we're working on a project on the Delft campus called the Daphwell, the Delft Geothermal Project well, which is a living laboratory, is the idea. And the idea of this is it will provide more than enough heat for the campus, and so also some areas outside the campus area of all of the heat needs. But it will also provide us as a working project where we can do quite a lot of science on. This causes us some wonderful opportunities because it's not often you can play with these real projects in such a way as we will be able to. But it also causes us some headaches because it's only one project and we have to make decisions of how to work on this project, how to design the wells so we don't actually damage any of the other side's, let's say, priorities. So we have some really good partners. We have EBN, Hydreco, Geomech, and Shell who are working with us. They're working together with TU Delft on the operations or the more commercial side. And then they're also helping us out on the science side, where we have a series of different objectives. We've had to be very careful about separating finances, separating activities, because neither side is allowed legally to pay for each other's parts. And that causes quite some difficulties, but we will get over those. We're lucky enough to have a fairly large grant called EPOS-NL, where we have about 6 million euros worth of research money to fund what we'd like to do in this well. And it also provides the opportunity of others to gain the data and others to suggest things we can do within the well. We also have a series of other projects that give us what I call operation funding, and that tends to mean PhD students or postdoctoral researchers that are actually able to do the research with the infrastructure. We have some fairly basic research questions that we try and answer in different ways. And the first is, well, how much energy can be delivered? And that's a very easy question to answer in a very superficial way and quite a difficult question to answer in a comprehensive way. And what we'd like to be able to do in the end is be able to predict how much energy will be delivered, not just on day one, but throughout the entire, say, several decades of the project. And how would this also be delivered if you had other projects nearby also changing their operations? So this leads towards a detailed characterization and detailed models. We'd also like to know how you can best monitor geothermal projects. So what do we need to measure to tell us how the projects are changing, to tell us how the longevity of the projects, to tell us what surface impacts will happen, etc. And then also, how do new materials or how do existing materials perform? So what do we need to know about geothermal fluids? How corrosive are they? How do the materials we put inside our wells react? What about clogging? What about different materials? What about the heterogeneities, etc.? So they're all questions that help us lead towards, in the end, how much energy can be delivered in the long term. What this means is we have more sort of, if you want to turn this more into research activities, we do quite a lot of work on the modeling, understanding the behavior, the thermohydraulic, chemical, mechanical behavior. We're planning to take quite some cores, which I'll tell you about in a minute. We're planning to do quite some considerable monitoring, both in terms of fiber optics, downhole, and in terms of monitoring around on the surface. And we're going to be testing quite a lot of materials and measuring the impact of the activities at the surface. And one of the things it's quite nice that for geothermal energy to really make a difference in this 50% of heat that I showed you before, we need to deal with cities. We need to bring geothermal energy into the urban environment. And the campus is a perfect, let's say, city that's kind of under control. So there's fewer stakeholders, fewer decision makers, which really means we can try to look at this integration in the urban environment. Now, I've talked about this project a bit. The project is still under development, so I can't show you photos, but what I can show you is some pictures of how we're planning to look at things as this sort of system develops in the future. This is a picture of our campus. It looks nice, green and sunny. That's not how Delft looks that often. It looks green because it rains a lot. And this building here is our current gas-fired power station. And this provides a certain amount of electricity for the campus, but provides all of the heat for the campus. And what we're planning to do is install a geothermal well right in front of this building. We're planning to go down to about 800 meters, deviate and go down to about 2,000 meters with about 1.5 kilometers separation at reservoir level. We're planning to install fiber optics behind the casing on the injector and going down into the producing well to do well testing as we go along. The coring that we're planning to do, please ignore all of the detailed text on the lithographic column on the left. I will tell you about the important bits. But we're planning to do coring throughout the whole overburden, more or less from surface right the way down to reservoir level. So we're planning to, of course, core the reservoir. We plan to core the entire reservoir, part of the overburden and part of the underburden. So we can really look at things like the heterogeneity of the systems, and we also have quite some cores then for doing different geomechanical and different studies. In the next well, in the injector well, we'll core certain parts of the overburden, so we really get an impression of various different depths, what will happen. What you actually find in the Netherlands is we know quite a lot about the shallow part. We know quite a lot about the part at around 2 kilometers depth because of oil and gas exploration. We don't actually know that much about this part because it's been drilled through basically as quickly as possible to get down to what was the more interesting parts at those times in the past. We also core some of the shallower subsurface in a monitoring well, in a separate monitoring well. And I'll tell you a little bit more about the purposes of that, where I show you a few more details of that sort of sub-project. Okay, so what we're also planning, and you'll see that this figure looks a lot like the old figure, except there's some monitoring wells surrounding the system that I've shown. And we're planning a seismic monitoring network around the well project. So what we can actually do is try to identify really very small seismic signals that are happening due to our project. So we're in a low seismicity area. We don't anticipate causing any noticeable seismicity, but what we want to do is monitor very, very carefully the background seismicity prior to the project starting, during the project implementation, and of course during the lifetime of the project. We have these different wells in yellow. They're all wells at around 200 meters depth, except for this one that will be around 500 meters depth. And the idea of putting them at depth is that you're insulated away from the noise at the surface, so you can detect lower magnitudes of events that are happening. This 500-meter well is actually quite a substantial project in itself. So what we're trying to do is collect shallow cores. We're trying to get detailed geophysical logs from this shallow subsurface. We want to install geophones at 500 meters depth, and also in shallower wells at 250-meter depth close by. And we also want to do some pumping tests at 500 meters. So that sounds like a lot. Why are we trying to do all of this? Well, the first aim I told you about was monitoring seismicity. That's what the geophones are there for. We also want to core for several different reasons. So one of the key reasons is for high temperature storage, which is what I told you about earlier. High temperature storage will help us bridge the gap between a geothermal well, which can supply constantly over time, or and the very seasonal heat demand profile. We're also going to core a whole package of clays here, which provide an important cap rock, but also quite an interesting geological age in the Netherlands when there was quite a lot of erosion, deposition, and it's quite geologically interesting what we can do in that layer. We're also going to take some even shallower cores, which are also designed for examining high temperature ATES. These ones are going to be quite challenging because they're not very well cemented. It's more or less a sand aquifer rather than a sandstone aquifer. Okay. You'll see a few slight differences in all of these figures, and I'll flick through some of them fairly quickly to tell you what's going on, because I also see time's running. We're also going to extend our heating network out towards the city of Delft, and we're also going to install some water quality monitoring close to the well location. In the longer term, we intend to install a high temperature aquifer thermal energy system, as I mentioned, around the well location. I'll show you a couple more details of this. And so I talked about this uneven heating profile. That's what this blue line is showing. It's the heating profile of the campus. And you can see in this red kind of shading here, this is what the geothermal well is projected to produce. And what we can do is basically take out this part here where we have excess heat. We can store it in the ground, and we can actually supply then these parts on both of these kind of shoulders here during a substantial part of the winter. What that does is it helps us reduce our peak gas usage by quite a considerable amount. So the geothermal well, we think, will reduce our CO2 emissions from heating by about 60%, and the HT-ATES will further reduce them by about 30%. It also increases the useful heat that can be supplied by up to 70%. What this allows us to do is to really get more out of our expensive deep geothermal asset, and so it actually helps the finances of the project really quite considerably, although also being a research project. In the very long term, and this is my second to last slide, Hadi, before you get a small heart attack, is to install an even deeper monitoring and exploration well in between where the two wells enter and exit the reservoir. So the idea of this is, after 30 years, we may indeed, this project is a heat mining project. It would likely run out of heat. We might need to look at other opportunities for heat. So it allows us to explore deeper potential geothermal reservoirs. And it will also allow us to install at depth much more instrumentation. We intend to test out some fairly novel geophysics, where we should be able to actually detect the hot and cold front, not just as it passes by this point, but actually in full 3D space by installing sensors within the borehole above and below where the heat front will come through. So that's quite an interesting, exciting project, but is certainly one for the future. Will not be installed in the next few years. And with all of these things, what we hope to create is what I'm calling an urban energy laboratory. And I'm trying to make our campus a geothermal campus. And what I hope that will do is turn it into a geothermal world. That's the end of my presentation. I look forward to any questions that you may have.
Thank you very much, Phil, for this very interesting presentation. Quite exciting movement that we are bringing geosciences just for the service of the city of Delft and seeing just across our buildings some real geothermal well. Things that we teach in the school now, we can just do that. And it's quite exciting. Sebastian, many questions. Are there plenty questions already being posted? Please.
Yes, Phil, thank you for super talk, and it's absolutely fascinating to see what's happening there. Delft, it's really the only place in the world that is sort of so advanced in terms of its urban energy, geothermal thinking, on really using the campus for as a living laboratory. Plenty of questions. I think quite a few from colleagues at Delft as well, who took the opportunity to learn more about what you guys are doing secretly. So we'll start with one from Sarah Beahani. What makes the Netherlands to be so interested in ARTES systems, and why are implementing them? So why is ARTES so successful in the Netherlands?
Yeah, good question. I think there's three reasons probably. One is that we actually have a relatively balanced heating and cooling demand. So if you have just heating or just cooling needs, then an ATES system, which is a storage system, fundamentally becomes quite difficult. So you need a balanced heating and cooling demand. So you can sort of draw a band around the world at this sort of latitude, and you can gain an idea of where is a good spot. That's one reason. The second reason is the hydrogeology, the subsurface. The Netherlands is in the end a river mouth, and you've had seas and the coastline moving backwards and forwards constantly over a long period of time. And that means you've got lots of aquifers that have some sort of confinement. So you have nice sandy aquifers, you have clay stones above and below. So you have a good hydrogeology. And the third is, because it was good, because of the other two, you have an industry that started. And that means that once you have expertise in industry, then it can move forward and forward and forward. And so now it's probably more or less the cheapest and fairly easiest solution if you have a heating and cooling demand and you don't want to use gas. So I think for those three reasons that all sort of come together, it's a good spot. Oh, you were talking, Sebastian, but you were muted.
Sorry. Thanks, Hardy. Someone managed to was able to mute myself here. Is there anything? So, as a fourth point, that the government has done specifically to provide whatever seed corn funding or underwrite some of the geothermal projects, or did this sort of emerge?
Well, I think there is funding schemes, subsidy schemes for sustainable energy. I think one of the things that helps with ATES systems particularly, and this isn't for the deep geothermal projects, for ATES systems, you can get a license within 6 weeks. So there's a very streamlined way of making applications, of knowing what data, knowing who you have to approach, and actually getting the permission to do something in quite a short period of time. And that comes a bit with experience. It comes a bit with having all of these projects that's gone on before. So some of the sort of front runner projects have had these difficulties, but I would say that the government and industry have come together to actually make it quite streamlined, and it works quite efficiently. What you do see now is, because there's so many in the Netherlands, we need to do more planning, better planning, because in some places you have a very congested subsurface with these projects. So what you of course want is to have them so they don't adversely influence each other, and in fact you have benefits from the other systems.
Thanks, Phil. Lots of questions from your colleagues in the department. I'm going to pick and see you had brought, I think, some colleagues who also help you answer questions. Martin Blomendahl has been really good at answering some questions for you.
Hey, Martin.
Marty Bone is really interested in the energy price. Just a bunch of questions. I'm going to try to group them a little bit. So she wonders how much are energy piles used in practice? Do the structures need constant monitoring, such as corrosion? What are the challenges of scaling them up? And are there any design parameters that we can use to optimize them?
Yeah, so energy piles are not that brand new an idea. They've been talked about for quite a long time, and in fact, they're quite a simple idea. You put some plastic pipes inside your sort of geostructures, your foundations, your piles, but they weren't used extensively for several reasons. One is that typically your piles weren't long enough; they didn't get enough heat area, let's say, heat exchange length. And as buildings become lower energy now, that's changed, and buildings now also need heating and cooling, so it's more, they have lower energy demands and balanced energy demands, and that means energy piles work much better than they used to in the past. So I would say that now is the time. So, and it isn't, there's some in the Netherlands, there's not that many in the Netherlands. The partner that we've been working with that's installed the test piles, so not the sheet piles, but the test concrete piles that we've been testing, has just sort of used our experience and some of the research results, and has installed 500 for a new development. And that new development was finished, some months ago. People are living there now, and they seem very happy with the results. In terms of monitoring, what you'd expect to see is as things get hotter, right, they tend to expand. So your pile wants to do this, and it wants to do this a little bit over time. It's a relatively small amount, so you need to take this into account in your building design. So you don't want to have a building that really can't cope with millimeter level deformation. And what you probably want to do is measure over multiple years whether you're getting any slow cyclic effects. In terms of corrosion, it's within plastic pipes that are generally sealed. You'll notice if you get a leak because you can't keep the pressure in it, but it won't affect the concrete pile itself. It's not going to corrode the actual the pile itself. It may just stop working. And of course, what you need to do is design it properly so you can switch, say, isolate one pile and switch it on and off. What we've been doing in the Green Village, which is a site on campus I didn't mention, is we have a single pile and we have a building on piles, and we're monitoring what happens with the temperatures and what happens with the deformations, etc. So we can find this out a bit more. What I didn't show you too much about the energy key wall is what we've also been monitoring is the inclination. So we had some small tubes welded to the pile, and we put down inclinometers over regular times during the test, so we can see whether it's actually rotating or if it's moving slightly, and exactly what way to try to eliminate the possibility of any adverse structural effects. What we see is that probably they're much more minor than if you, for example, backfill it with sand. You get a much greater impact than if you change the temperatures.
Thanks. There are a lot of questions in the chat around sort of the geochemistry and what happens if you, during thermal aquifer storage, you heat up the subsurface. What chemical reactions are happening? Does it affect microbiology? Putting, and again, Martin has been quite active answering some of the questions, but I'm putting one from Trevor Atkinson forward. So what type of geochemical modeling is being done to evaluate downhole geochemical reactions?
Yeah, and I'm not a geochemist, so I have to say I probably will give you a fairly superficial answer to this. So I think it depends on what sorts of system that you're looking at. So the ATA systems that I mentioned that we have a lot in the Netherlands are restricted in temperature. So they're sort of restricted to 25 degrees. But the high temperature ones that I talk about, and I say it depends what you say by high temperature, for different people means different things. High temperature aquifer thermal energy storage is anything above 25 degrees because it's then different from your typical ATA systems. And they're being starting to be studied at the moment, taking samples, looking at what happens. And so, of course, as you increase your temperature, you increase the possibility, you increase your kinetics, you increase change the equilibrium conditions, so you increase the likelihood of adverse geochemical reactions. So it's a point, especially with the high temperature storage, we need to take quite a lot of care of. For deep geothermal projects, scaling, clogging, etc. are a key thing in general. So we don't want to clog our reservoirs, clog our pipes. The typical conditions that we would see in the Delft sandstone that we're aiming for don't lead to significant concerns in terms of scaling. But what we do intend to do is take regular samples right at the beginning of the project, and as things over time, also to keep track of any changes in the reservoir that we can detect via the geochemistry. I said it was going to be a slightly superficial answer, and it was a slightly superficial answer, I have to say.
Are you worried about the Daphwell that there's going to be scaling, or is it sort of
no? For the Daphwell, there's a couple of other projects nearby. So not pilot projects that are instrumented to the level that this one will be, but there's a couple of other projects in the same reservoir, and they don't suffer from scaling or clogging. So in that sense, we have quite good experience and quite good expectation that we won't have serious clogging conditions.
So Yuan asked the question that Young-Wang asked the question that's probably on everyone's mind: when are the Daphwells being drilled?
Yeah, good question. Well, if I was fully in charge of everything, they'd be already drilled. But unfortunately, as every academic realizes, that we're not in charge of everything. But there's our provisional date now is at the end of the summer next year. There's a few things that have to come together to make this happen. So as with all geothermal projects in the Netherlands, we rely on the government subsidy to make it financially viable. And as I said, the project partners, including TU Delft, that invest in the project need to have a financially viable project. So that's one of the barriers. But everything else is lined up for an August start date. So that's the provisional date. I've said it now, so it has to be true, right?
Fingers crossed. Yeah, lots of questions. So here's one from Jingqi Zhang, and says, can you say a few words on what methods you use to obtain subsurface thermal properties? You mentioned lots of cores that have been collected. How do you go from the local measurements to regional properties?
Yeah, so it depends on which system, again, you're talking about. And to some extent, which is maybe strange, is the deeper subsurface is a little bit easier and the shallow subsurface is a bit more difficult. So I'll tell you a little bit about both of them to some extent. So the shallower ones are the ones we've been working on and developed some new methods. So the typical way of measuring thermal properties or at least thermal conductivity in an easy way is the needle probe test. That's the one everyone knows about. You stick a needle in a sample, you apply a constant power, and you look at the semi-log plot, and you derive the thermal conductivity. That's great if you have a sample at surface, and as soon as you're looking at soils that tend to deform as soon as you sample them, it's not very good. You don't get good results. So we've been developing two different techniques to get us better information on them, and both using cone penetration tests, which are a typical geotechnical subsurface test. And basically, you push a cone through the ground, and you put some sensors on it and measure the response. One of the things in the very early days of this test that caused quite a lot of problems is it heated up as you do so. You get quite some friction, and it caused a lot of the electronics to kind of drift off the measurement and cause some problems. They solved that quite a long time ago. But what this means is you get an opportunity to watch it dissipate. So if you simply put a temperature sensor inside as well, you push it down, it heats up, and then you stop. You watch it dissipate, and effectively you have, well, some sort of needle probe, and you need to do some slightly different maths, but you can get the in situ values point-wise as you go through the soil. So we developed this method alongside a different company called Fugro. And then we also looked at trying to get continuous profiles in the shallow subsurface by correlating these CPT readings of the other sensors with the thermal conductivity. So that's been quite successful, and that's being used in fact, mainly for offshore measurements for high voltage cable design at the moment. It's being used around the world, so that's quite nice. In terms of at depth, there's quite some coring, and I think geothermal in the Netherlands particularly and around the world is benefiting from the oil and gas industry. And I have to say that quietly, right? So people don't accuse us of greenwashing. I've never been in the oil and gas industry, so I can say this. But billions and billions of euros or dollars or whatever have been put into exploration, coring, etc. The Netherlands has had 5,000 wells at depths greater than 2 kilometers. So we have quite a lot of property samples. We have quite a lot of information from down there. And that means that the thermal properties are actually pretty well known from coring. And coring at depth, of course, they don't fall apart. So that's a bit easier. And you can bring your samples to the lab and do quite a lot of measurements. We're also quite lucky in the Netherlands to have a lot of public data, and our sort of geological surveys, so T&O, have a system online called ThermoGIS, Thermal GIS, and actually they've compiled quite a lot of these properties in across the full country, the geological layers of interest for geothermal, and you can actually go and basically look at those, and they're all based on information that's been obtained from oil and gas exploration.
Thank you. We probably have time for at least one more question. Go with Edgar Hernandez, and he wonders: is it not an alternative option to drill hot, cold slanted wells to improve their productivity and cope with heat demands, and simply stop the ESP during the summer instead of doing high temperature aquifer thermal energy storage?
Yeah, so there's several different ways of operating your system. Let's say you could. So my sort of premise that I very briefly said was that the best thing to do is operate your wells as hard as possible, get the heat out, and then keep it for future use. And of course, another option could be to simply stop. And there's some reasons, both technical, economic, and probably political, why that why my method is maybe optimum, let's say, or maybe in my view at least better than simply stopping. And let me go through them sort of one by one, and hopefully I don't forget them as I go through. So what you actually find is, say, in the winter, your peaks are really quite high. So just an example from the TU Delft campus, our geothermal well we propose with the DT that we propose at the minute to be around 7 megawatts, whereas our winter peak is around 30 megawatts. Okay, so it's around 3.5 times as big as we can supply through our well. So what that means is if I store the heat from the summer, then I can actually store it in a much shallower, much cheaper system, and I can have many more extraction wells. So that means I can actually provide most of my peak, which means I can remove a whole bunch of the gas peaking that's needed. And with these shallower wells, I can also switch them on a bit more easily on demand, so I can also follow some of the peaks, right? So it's a bit more of a flexible system. So that's probably one of the technical reasons. Another technical reason is probably that your well materials corrode, degrade over time. So you have a finite lifetime of your system. So what that means is you probably need to run it reasonably hard, let's say, so that you can get the heat out so it has enough value to pay for your system. That's probably the sort of technical systems. Of course, you could argue a little bit, yeah, you could put the spacing closer together, but then you're drilling more wells, which increases the cost. There's a social political reason that comes down to the length of the subsidy that you get in the Netherlands, which is 15 years. And that means that after 15 years, your system, the heat you produce, is much less profitable. And so that means there's the way the government has incentivized the system means that actually you really want to drive your asset as hard as possible in the earlier period to maximize the subsidy and in fact have a affordable project. So that's probably the second reason. I think I've probably forgotten one or two, but that's at least half an answer.
Great, thank you. And that takes us exactly to 4 p.m. So Phil, thank you very much for a great talk. There's lots of further questions in the chat. I think quite a few from your colleagues, so you know where to find Phil. It looks like you're in your office at the moment. Just go and knock on his door and ask him the questions. Definitely looking forward to seeing what is happening to the Daphwell and when it comes live and how it all goes. And fantastic project. Great to hear from you, Phil, about the project. And over to you, Hadi.
Yes, thanks very much, everyone. I'd like to just take the chance, introduce our next week speaker. Next week, we are going to spend the webinar on a very important subject, as important as the technical subjects as Phil just presented, but also next time will be about diversity. So we have two guests next week, Joshua Atkins and Louisa Bailey. Joshua is from Energy Networks. Louisa is from OVO Energy in UK. And they are going to talk together. So we are going to have, for the first time, two speakers at the same time, going to jointly speak about delivering inclusivity for LGBTQ plus people in the energy sector. So I hope that all of you mark your calendar to be with us next week. The same time, 4 p.m. Central European, 3 p.m. British time, and 7 a.m. California. Stay happy, healthy, and tuned in to the Geoscience and Geoenergy channel for another talk next time about diversity. Thanks a lot, Phil. It was quite an engaging and a lot of discussions took place. Thanks.
Thanks a lot. Thanks for the invite.
Thank you. Bye-bye.
Bye. Bye, everyone.